So now that we see that we have to start looking at the individual molecules in a substance to really gain an understanding of temperature, we need to return to the idea of Avogadro's number, which is a way of thinking about going from the mass of an object to the number of molecules that are in that object. And so Avogadro's number defines the number of molecules in 1 mole. Or that is to say that 1 mole contains an Avogadro's number worth of molecules. Now you could use Avogadro's number for anything. You could also use it for people, cars, houses, trees. But the way we specifically want to use Avogadro's number is in a chemical sense to count the number of molecules in a substance. And although this is just a little historical note, how did we actually pick that number? Well, it was decided that 1 mole would be the number of molecules in exactly 12 grams. And I mean 12.0000 on for infinity, 12 grams of carbon-12. And it turns out that if you had 12 grams of carbon-12, you would have 6.022, and the number is actually even more specific. You can look it up in your in tables, and they'll give you even out to 3, 4, 5, even 6 or 7 more significant figures. But for our purposes, 6.022 times 10 to the 23rd is good enough molecules. Now it also turns out that for a gas, that 1 mole of any gas, I don't care what it is, carbon dioxide, oxygen, hydrogen, argon, any gas, 1 mole of that gas at standard temperature and pressure, will occupy exactly 22.4 liters. Now, I'm sure that you've all seen a 2-liter bottle, and so 1 mole would occupy approximately 11 2-liter bottles. So 1 mole typically turns out to be a pretty small amount. I mean, even for carbon, for example, it's only 12 grams. 12 grams of carbon gas would occupy 22.4 liters, even though 12 grams is a tiny, tiny amount of material. So that brings us to 2 potentially useful formulas. And let me write those formulas for you. So our first formula relates moles to number of molecules, and that would be lowercase n is equal to n over Na. And in this case, n equals moles, big N equals number of molecules in the substance, and Na equals the number of molecules in 1 mole, or very simply, Avogadro's number. So if I wanted to know how many molecules were in a substance, the key to knowing that number, capital N, is I would need to know the number of moles. Okay, this is a fixed number, it's a constant, but I'd have to know this number of moles, to figure out this. Or by contrast, if I knew the number of molecules I had, I could calculate how many moles that I had. Okay, so that's one useful formula. Second useful formula relates the mass of a substance, the overall mass of the substance, to the number of moles and the mass of 1 mole, the molar mass. Okay, so M here is the mass of the substance, N, just like it was before, is the number of moles, and mu is the molar mass. So the molar mass would have units of typically grams per mole. Could be kilograms per mole, but turns out moles are pretty small. Even the largest atom that we know of still is less than 1 kilogram per mole. It's only about 238 grams per mole. All the others are much smaller than that. They might only be like 12 grams or 1 gram for hydrogen. Very, very small. So the molar mass is going to be in terms of the number of grams per mole. So if, for example, I know the molar mass, and the molar mass can be found typically on the periodic table, I would simply go to the periodic table and look up the mass of the atoms that make up that molecule, and then I would be able to figure out what the molar mass is. So this is something you can look up in a table. What I need to know, though, is the number of moles, and I can calculate the mass. Or if I know the mass, I could calculate the number of moles. If I knew both of these two, the mass and the number of moles, then I could calculate the molar mass without using the periodic table. So let's look at an example of that's in the textbook. This is the sample of oxygen gas, and in this case oxygen does not come by itself. Oxygen as a gas is always a diatomic molecule, meaning that there are always two oxygen atoms combined together. And so if I looked up on a periodic table, I would find that the molar mass of one oxygen was 16. So this means that the molar mass is equal to 32 grams per mole. Okay, and I think oxygen is actually about 15.999, but we'll just use 16 for this example. And in this case, we get a molar mass of 32 grams. I see that I have a number of molecules of 1.2, so this would be my N is 1.20 times 10 to the 25th. And what I'm effectively going to have to do is to kind of combine the two equations that we looked at together. I could do this in 2 steps, or I could do it in 1 step. All right, so let's do this in 2 steps for this first calculation, and then the next one we'll go ahead and do. We'll go ahead and make the transition all in 1 step. So I have N. Now my link between these two things is little n. Okay, so what I have is the information necessary for this equation. That will give me N. I'll go from N to this equation where I know the molar mass, and I'll calculate the overall mass of the substance. So effectively what I need to do is use this equation that N is equal to big N over NA, and that's going to be 1.20 times 10 to the 25th divided by 6.022 times 10 to the 23rd. And in that case, that's going to give us approximately 19.93 moles. And then from there, I'll take this and plug this into this equation to calculate the mass, where I know that M is equal to little n times mu, so that's 19.93 times the molar mass of 32, let's just leave the units out of there, grams per mole, and so I end up with a total mass of approximately 638 grams, or that would be 0.638 kilograms. Okay, so let's take a look at another example. And this time I want to do it a little bit different. This example is basically the opposite, the reverse of the previous example, but I'd like to do it a little bit of a different way. I want to do it all as one calculation, and I don't want to use the equations. I simply want to look at the units for the numbers and do these sort of conversions. Now in this case, I know that I'm starting with a mass of 1.0 kilograms of uranium. I also know that the molar mass of uranium is 238 grams per mole. So what I would do is start with 1.0 kilogram of uranium is a capital U. So my first step is I can't convert to number of moles until I put everything in terms of grams. So in order to do that, what I know is that 1.0 kilograms would be equal to 1,000 grams, and my kilograms cancel. Now what I also know is that there are 238 grams in 1 mole of that substance. I also know that in 1 mole there are 6.022 times 10 to the 23rd atoms or molecules, and that's it. My kilograms canceled, my grams canceled, my moles canceled, and all that is left is number of molecules. And so by making this calculation, so in this case I only worry about the things where there's not a 1. So I see lots of 1s that I don't need to worry about. I need to take 1,000 times 6.022 to the 23rd divided by 238, and that gives me 2.5 times 10 to the 24 atoms of uranium, and that's it. Now, this technique is much more useful, I think. You don't really need to it doesn't require any equations. You just simply think about the units. Grams, sorry, this was grams per mole. So grams per mole, I could put 238 over 1. 238 grams is equal to 1 mole, or I can flip it over and I can say 1 mole is equal to 238 grams. In other words, these two numbers could be flipped top or bottom depending on which calculation I was making. Had I started with number of atoms, then I would have had this thing flipped over. Okay? So each of these conversions, kilograms to grams, moles to grams, or moles to number of atoms or molecules, these are things that can be put into a conversion and simply spit out the answer at the end. And so this is our final answer.